Okay, let's wait and start. Okay, started. Okay. So this was for water. This is liquid. This gas. This solid. And just to summarize what we were saying last time, the solid lines correspond to first order phase transition. We will see why we call them first order phase transition. But the thing is that at this level that they separate two phases which are clearly different from each other. So for instance, ice and liquid water are clearly different from each other. And you can find what is called a mixed phase, in the sense that you have the fixed value of pressure and temperature, and we will see also chemical potential. You find that it's these two phases, they coexist in a mixed phase, although they are completely different to some extent. So these solid lines separate the phases, and for each point belonging to the solid line, so to the solid lines, you have a different state of a mixed phase. Okay. Then there is an intersection here of three solid lines, which is called triple point. And there is another point here, very interesting, which is called the critical point, in which you basically lose your separation of phases between liquid and gas. So above this point, there's no clear difference between those two phases, whereas below this point, there is a phase separation. Okay, this is called the critical point. Now this is just just for water, but actually it's a schematic phase diagram, in the sense that the phases are more than that, and these are the most famous. Now, we were also saying last time that if you look at the PV diagram and you draw the isotherms or the isothermal lines, then the way they look like is something like that. This is for T larger than Tc. Then there is a line for which T is equal to Tc, for which we have a point in which the pressure, the derivative of the pressure with respect to the volume is equal to 0. And then there are the lines in which we have the mixed phase, so something like that. This is T below Tc. Something like that. I'm not very good at drawing, and you can actually connect these points up to the critical point. It's a typical diagram that you find in books. And all this region here, or the phase of the PV plane, below this dashed line, basically is the region in which you can have a mixed phase. Okay, so this region here, I'm just doing repeating this plot. These are the mixed phase. Okay, the mixed phase here does not correspond to a region on this diagram, it's just a point. Whereas here you have a region in the PV plane in which you have the formation of this mixed phase for the different values of the temperature. Now, it's clear that if you compare those curves with the curve that you have for ideal gas, there's something that we are not really catching here, no? Because for a real gas, let me see, maybe I can write until this line here. For ideal gas, clearly, in the PV plane, what we we have is something like that. P V for ideal, just an hyperbole, no? Because it's PV times equal to KBNT. So there is something here that the ideal gas is not able to describe, of course. Now, we'll see this later in the context of statistical mechanics, but we can do here already something which is introducing some more physics in what is called in the physics of the ideal gas, which is very trivial. Okay, we will see later that the ideal gas is nothing but basically the assumption that the Hamiltonian you are dealing with is just made of kinetic terms. Okay, so what we have to introduce in order to have a richer structure of the phase diagram and also this kind of phenomena is to introduce interactions between particles. Okay, and those interactions can be included in a phenomenological way in a model which maybe you have heard of, which is the van der Waals model. We will do this by following the procedure of van der Waals, which is a phenomenological model. Phenomenological model of van der Waals. Let me see how to write it because I always forget. Okay. It's called also a real gas equation of state of a real gas. You have any experience with the van der Waals gas? Maybe some. Maybe you have heard about this. Okay. Now the idea is the following: consider a typical kind of interaction that you have between typically between particles or between molecules in a system which is any macroscopic system. So typically, the kind of interaction that you have is something like that. Let's draw a kind of potential and a distance between particles, and a typical shape is the following, which is attractive at large distances and repulsive at small distances. So there are two features in this potential that we would like to describe or to model. So which is attraction, attractive for, let's say, large distances. So it could be, for instance, the polarization, electric polarization of molecules. No, if you have dipolar molecules, that the dipoles orientate in such a way to have traction, and typically they have repulsion instead. Repulsion at small distances. This repulsion, in the case of atoms, could be the repulsion between the electronic clouds, for instance. Or if you talk about neutrons or, well, nucleons, neutrons and protons, also in that case, there is a potential like that, in the sense that you have attraction, binding at large distances, whereas you have repulsion, hardcore repulsion, when the distance is very small between those particles, okay? So these are, let's say, general feature of the interaction of microscopic particles. It's a very common, let's say, kind of potential. One possibility to describe such a potential is, for instance, the Lennard-Jones potential, which is used in the context of, say, chemistry or solid-state physics, which is the following. An example. Lennard-Jones potential, which has a repulsion and an attraction done in the following way. V of R, the potential function of the distance between the particles, is a certain parameter A divided by R to the power of 12, which is the repulsive term, minus B divided by R to the power of 6, where A and B are two parameters characterizing the interaction. Okay? You might have seen this potential maybe last year when doing studying the structure of matter. Maybe, I don't know. Now, of course, here you have a potential which, although having a, let's say, analytical shape, analytical formula, it's a little bit complicated to be introduced in the calculations. We will actually see later, much later, that there is a way to introduce interaction, at least the first order correction to the just the kinetic terms in what is called BDL expansion. But at the moment we are following a procedure which is much easier, which basically we basically assume those two main features of the interaction potential, but we model them in a very simple way. Well, that actually is not our idea, but it's the idea of Van der Waals. So, in particular, let's deal with the repulsion, the repulsive part of the potential. So, in the Van der Waals gas, one assumes that the potential is so repulsive at small distances that basically below a certain size, below a certain distance, the potential, let's call it D, V of R goes to infinity if R smaller than D. So we have basically something like that. Suppose that this is D, and here the potential explodes. Well, something like that. Okay. And there's no way for those two particles to interact or to be closer than D. Okay, there's just an infinite potential that does not allow the two particles to be closer than D. Okay, so this is, if you want, hardcore size. D. And the effect of this is basically to reduce, so that basically means that the particles occupy a volume, no? A finite volume, which is provided clearly by this distance D, and therefore the total volume available for the particles is not the volume of the, say, box in which we have those particles. So this V that was the volume for ideal gas. Must be substituted by the volume, again, of the box, minus a certain number that is called B, that provides a correction to the volume, which at the end basically provides me an effective volume that can be occupied by the gas, by considering the fact that the particles have a finite size, and they have this finite size due to this hardcore repulsion acting at a distance d. Okay? So the effective volume is actually V minus a correction B, where B is a parameter in which we put, is a carpet under which we put the physics that we don't know. Okay, so B contains the microphysics that we don't know. So the shape of the potential, the typical, I don't know, those two parameters of the Lennard-Jones potential that were A and B. So this constant B somehow takes into account the microphysics of the interaction and specifically of the repulsive core, of the hardcore repulsion. Okay. Now this is for what concerns the repulsion. So we have to, let's say, modify the volume available for the particles to be V minus a certain B, which contains the effect of the interaction. Now, what happens with the attractive part of the potential? Now, this is more complicated, and basically the argument works in this direction. Suppose that you have a very, very attractive potential, and if it is very much attractive, then what happens is that your gas is actually self-bound. So let's write this for very high strength of the attraction. The gas will be self-bound. Self-bound means that there is no way, there is no need to have a box that contains the gas, no? So the interaction is so strong that the particles stuck to each other. So there is no need of having a box to contain the gas. Okay. And self-bound means also that the pressure of the gas approaches zero. Because if you have a finite pressure, then of course a gas with a finite pressure will try to expand. Well, finite pressure with respect to what? To the environment, okay? So a pressure which is larger than the pressure of the environment. So a gas in vacuum, of course, will expand because it has a finite pressure. But in this condition, in the limit in which you have a very large attraction, this system of particles can be self-bound. There is no pressure, and therefore the system will just stay in its initial state without any expansion. Okay, so this is a very extreme case. Actually, what happens in reality is that anyway, this is the limit in which the attraction is large and the pressure is going to zero. But what we need qualitatively to introduce is therefore for a real or for realistic traction, we have somehow to introduce, to reduce the pressure with respect to the case of the ideal gas. Okay, so in a similar way in which we reduce the volume due to the finite size of the particles, and the finite size is provided by the hardcore repulsion, we also need to reduce the pressure that we had in the ideal gas equation of state that takes into account the attractive part. Okay. In particular, the pressure, well, this is isotropic, the pressure, but basically, okay, let's write first the formula, then we derive, well, we provide some explanation for that. So anyway, the argument is that we need to find a way to reduce the pressure of the ideal gas in some way. Now, the way van der Waals does it is to correct the pressure in the following way. So we write the pressure P as the pressure that we write kinetic, which is actually the pressure of ideal gas. And for what we said before, we need to reduce this pressure. And van der Waals introduced a term which is done in the following way. This is A, which is again a constant that depends on the gas, in which there is the microphysics that we don't know. And here there is a correction, which is 1 over V squared, where V is the volume occupied by the gas. Okay. So again, A is a constant containing the microphysics, and B is the volume of the box. Volume of the box. So there is a minus there, and now we need to somehow model, well, to justify how does the dependence 1 over V squared come from. So now this formula that I'm going, well, this kind of equation of state we are trying to work with will be justified in a more deep way when doing the canonical ensemble and introducing the virial expansion. Now we can just provide some phenomenological arguments. So, such as the case for the volume, we say that we have to reduce the volume, now we have to reduce the pressure, and we need to introduce this 1 over V squared term. Why 1 over V squared? Now we can provide just, for the moment, just a sort of phenomenological explanation to that by considering the following argument. So now let me make a draw. Suppose that this is my volume occupied by the gas, or better to say the volume of the container. And let's introduce a layer close to the surface. So suppose that this is the surface, surface. And we have a layer having the size of the interaction of the typical intermolecular. Sorry, with the mask is even more difficult. This is the typical distance of the interaction, okay? So let's call it RA. So this is RA. So this is the scale of the attractive interaction. What is the scale? In the Lennard-Jones, we had something like that, so something like that, okay? So this is the scale, the distance at which the attractive potential has the maximum of the strength, okay? So this is P1 RA. So within this layer, particles feel the attraction, and therefore, by feeling the attraction, they exert a pressure, a reduced value of the pressure to the wall of the box. Okay, so let's write in this way: due to the attractive potential in a layer of size RA, we need to introduce, or we need to reduce the pressure. So because here particles, they feel the attractive interaction, therefore is this layer responsible for the fact that the pressure of the gas to the box is smaller with respect to the pressure of the ideal gas. Now, how to model the effect of this interaction for the energy? Well, let's write it this way: the potential energy which is associated with the attraction must scale as the number of particles that are in this layer. And in particular, since we are talking about a two-body potential, it must be proportional to the number of particles in that layer squared, no, because it's a two-body interaction term, and so we can imagine that the correction due to the potential energy is provided by the number of particles, so if you want, the number of pairs, okay, the number of pairs of particles that are in this layer, okay. Non si legge? È successo? Ah, ok. The potential energy associated with attraction, with attractive potential, scales, there is a sigma, proportional, okay, to the number of particles in this layer, okay, time squared. Now, what is the number of particles in that layer? Lo scriviamo qua. Now, this layer has a volume which is RA, so the scale of the attractive potential times surface. This is a volume. If I multiply the volume by a density, let's call it N divided by V, where N divided by V is the density of particles, and then we have to square. Okay, then we have to square this. So then it is proportional of sim2 divided by V squared. Okay, so what I'm basically doing is to count the number of terms, the number of pairs that we have in this layer. And this must scale as 1 over volume squared, and then we have n squared, suppose that is fixed, LA is fixed. Now S is not fixed, but it's a surface, and the effect of the surface on the energy is subleading with respect to the effect of the volume, okay? It's valid in general for large systems. So therefore, the main correction, having a finite system like this, the main correction due to the interaction is provided by 1 over V squared. There is a correction, of course, due to the surface, but it's subleading, okay, as usual in a thermodynamical system, which is a large system. Okay, so these are, I mean, one can be, let's say, to some extent happy at this level, but we will find a more deep or more general way to find the ideal gas, so the correction to the ideal gas later on, okay? At the moment, let's say that we have a phenomenological description for which we have to reduce the total volume of the gas due to the repulsive interaction, and we have to reduce the pressure. And the way we reduce the pressure is to count the number of particles that are interacting within this layer of scale RA, close to the surface of the box. This is reducing the pressure that the gas is exerting on the box. Okay. I feel that we almost done. So now we are almost ready to write the final formula, which is the following. So now we said that the volume of the ideal gas must be substituted by V minus B, which was an effective volume. And the pressure must be corrected also. We have to go from P to P equal to P kinetic minus A divided by volume squared. Now, the last hypothesis for number of moles n small n equal to 1 is that the two things that we wrote here are connected in the same way as the ideal gas, in the sense that one imposes that V effective times P kinetic equal to RT as the case of the ideal gas. Okay. This must be in this way, in the sense that then if we switch off the potential, we should recover the ideal gas equation of state. Okay. Now, to write it more explicitly, what we have there is that V minus B, which is the effective volumes, times P plus A divided by V squared is equal to RT. Okay. Now, this is the equation of state of van der Waals. Okay, so it looks similar to the ideal gas equation of state, but for the fact that we have now these two constants, A and B, we have a correction to the volume and we have a correction to the pressure. Okay, now of course, if A and B are equal to 0, we recover the ideal gas case. Okay, and A and B are phenomenological parameters. Sorry? No, but this is okay. This is just the starting point is an assumption of Van der Waals, is that V effective times P kinetic is equal to RT. Then P kinetic is P plus A divided by V squared. Okay. Now, of course, this is a phenomenological model that can be tested by experiments, right? And then we will see that actually this is the case. It works. Okay, then we will find a more deep explanation for that. Okay. But at the moment, this is the, let's say, phenomenological description that we can do at this level. Now we can play a little bit with this formula. In particular, we can write the pressure as a function of the other variables to get that the pressure is RT, where R is the universal gas constant, as usual, divided by V minus B. Then we have minus A divided by the volume squared. Okay, so this is the equation of state of a real gas, of Van der Waals gas. Okay. Now we can, by fixing A and B, we can work a little bit with this formula and write, and what time is it now? Dobbiamo finire oggi alle 11. Now we can draw the isotherms. Or the isothermal lines in the PV plane. Let's do it here. Now, this is a game that you can play, for instance, with Mathematica or with whatever software you like to do plots. You fix A and B, then you change the temperature and you see which is the shape of this function here. Now, what you will see is that it happens exactly, well, almost exactly, what we had in the case of the phase transition, in the sense that we have some lines like that, which are very similar to the case of the ideal gas. Then at some point, we have a curve like that, which corresponds to T equal to Tc, which can be determined, as we will see, as a function of A and B. So we have a line for which the derivative of the pressure with respect to the volume at some point is 0, which is a critical line. And this is T larger than Tc. We will see what Tc is as a function of A and B. And now you see the shape of this function. Here we have that the pressure as a term which is 1 over V, and here we have 1 over V squared. So it's a cubic in the volume, okay? Because you can, let's say, find for a fixed value of the pressure, you can have 3 different volumes here because it's a cubic, you have a cubic relation, okay? And therefore, indeed, as it happens in this case, for T smaller than Tc, what you have is something like that. So here, for T larger than Tc, what we have, one pressure, one volume. Here, for instance. And this holds true down to T equal to Tc. For each value of the pressure, just have one value of the volume. Below a certain critical temperature, you have actually this situation in which you have 1, 2, and 3 solutions. Okay, so for T smaller than Tc, you have one pressure and three volumes. Why? Because this is a cubic equation. Okay. Noi cancelliamo qua. Lo faccio adesso, lo faccio dopo, lo faccio dopo. So anyway, you see the structure of this, right? So you can multiply by, okay, this pressure is equal to RT divided by V minus B times B squared. And then I have a B squared here minus A times B minus B. And of course, now from this, you can guess that V squared V minus B times the pressure is equal to, well, the rest of the equation. So RT B squared minus A V minus B. And you see that this is a cubic equation in volume, okay? So you have an equation that once you fix the pressure and the temperature, okay, A and B are fixed, is a cubic equation, okay, with a term which is also independent on the volume, so it cannot be reduced to a quadratic equation. Now, remember this is a cubic, and remember also that close to, well, at the critical temperature, we have just one value of volume for one specific value of the pressure. So that means that at T equal to Tc, we said before graphically, we have for a certain value of the pressure, one value of the pressure, one value of the volume, for what we said before. Therefore, here at this condition, the equation, let's say asterisk here, or pallino, or vabbè, facciamo asterisco here, must be of the form V minus Vc cube equal to 0, where, let me draw again the line that we are considering, which is the critical line. Here we have T equal to Tc, so then this we call this Vc, and this we call Pc. Okay? So since at T equal to Tc, we always have, for one specific value of the pressure, we have just one solution for the volume. We need a triple root. So the form of the equation, the algebraic equation that we have there, must be of this kind. Okay. So from this you can get that B, well, we develop, you expand this. So you have B cube minus 3 with V squared Vc plus 3 Vc squared minus V equal to 0. Okay, so this is just due to the fact that we have one solution, and since this is a cubic, this solution must be a triple solution. So we have something like b minus bc to the power of 3 equal to 0. Okay, let's give a name to this equation. Let's call it 1. Now let us consider the equation state, which is this one, but close to the critical temperature and the critical pressure. So let's write in this way, close to the critical point, the equation of state has the following form: V minus B times, here we had the pressure plus A divided by B squared. We write critical pressure plus A divided by B squared. Then this is equal to RTC. So basically what I'm doing is to consider a region. Let's draw again this line here. This was the critical temperature, critical volume, and critical pressure. I'm writing the equation of state in a region which is close to the critical point, so here, which I move a little bit from DC, but I have TC and TC in that region. Now, if I expand this part, so the idea is the following: now to expand this equation, compare with this, and find a relation between VC, TC, PC, and A and B. Okay, so let's work a little bit. This what I just said. So this is V minus B. Then we have PC V squared plus A equal to RTC B squared. And now, okay, you can go on. You have PC times volume cubed plus AV minus B PC volume squared minus AB equal to RTC volume squared. So you work a little bit the algebra. So now you have a cubic term, a quadratic term, a linear term, and a term which is a constant AB. And you finally obtain, sorry, but I have to erase a little bit. You finally get, you work a little bit this equation, and you finally get the following equation. So B cubed minus B squared. Then here we have BPC plus RTC divided by PC. And we have plus AV divided by PC minus AB divided by PC equal to 0. Okay, so we divide by PC, we have a volume cube, then we collect the V squared term, and we have BPC plus RTC, which is here, then you divide by PC, and we have the linear term, which is this AB divided by PC, and the term minus AB divided by PC. Okay, let's write this equation 2 let's label this equation 2. Now 1 and 2 must provide the same solution. Therefore, by comparing the 1 and 2, so they are the same equation basically. Let me remove this. And let us compare 1 and 2. Let us compare 1 and 2. Now, of course, we have a cubic term 1 and 1, so we don't have any equation on that. We have to impose the term here, which multiplies the quadratic term in the volume, must be the same as in here. The linear term, which is A divided by PC, must be equal to 3BC squared. And this term here, AB divided by PC, must be BC squared. Okay, so you get 3 equations, which are the following. The first one is B plus RTC divided by PC equal to 3BC. Okay, which is basically this. Okay, so we have PC, we can remove. We have B plus RTC divided by PC is equal to RBC. Okay, just comparing 1 and 2. Then we have that A divided by PC is equal to 3BC squared. Let me see if this is correct. 3BC squared must be equal to A divided by PC. And finally, the final equation is that AB divided by PC is equal to BC cubed, which is just this. AB divided by PC is equal to BC cubed. Okay. Now, of course, now you can solve the system and basically find a relation between A and B and the critical quantities. So let us remove this. So you solve the system of equation, and you will find that BC is equal to 3B, PC is equal to A divided by 27B squared, and RTC is equal to 8A divided by 27B. Questo è 1, 2. Okay, so what these equations are telling me is that once we have A and B, we can compute the critical volume, the critical pressure, and the critical temperature. Or, in other words, if you measure from a real system those quantities, volume, critical pressure, and TC, you can obtain the values of A and B of the microphysics. Now, an interesting way to write the equation of state is the following. Now you can introduce P bar, which is equal to divided by PC. T bar equal to T divided by TC, and V bar is equal to V divided by VC. So these are, of course, either a-dimensional quantities, and write the equation of state in terms of these a-dimensional quantities. Now, by using the relation between VC, PC, TC, and A and B, one can show, I'm not doing the algebra because it's very boring, and you don't need to learn this, just need to remember that there is a way to write this in a-dimensional form, and you get the P plus 3 divided by V bar squared times V bar minus 1/3 is equal to 8 divided by 3 T bar. So you get, what is interesting is that you get an equation of state in terms of a-dimensional quantities, which are P bar, V bar, and T bar. There's no, let's say, sign here of the microphysics because A and B are hidden inside the scaling of the pressure, the temperature, and the volume with VC, TC, and PC. Okay, so these are sort of universal equation of state. Universal means that you can, in principle, apply this equation of state to several different systems. Those several systems will have different values of A and B, but if the kind of interaction is the same, you can find from A and B, TC, PC, and BC, and the relation between the pressure, volume, the temperature scale, the scale values of those quantities in a van der Waals structure must be the following. Okay? So this is an example of universality, which is a thing which is very important in this context of physics, because it basically provides some laws that are independent from the microphysics, okay, from the specific value of the Lennard-Jones potentials. Okay, if you have several systems with those kind of interaction, they actually behave. When considering the a-dimensional equation of state, they behave in a very similar way. And indeed, this kind of universality is present in the sense that is measured in the real systems. And now it's useless that I'm doing to make this plot here. By the way, this is a book of Wang. There are copies in the library, okay, if you want to have a look to this. Now I show you the plot of this, or the consequence of this universality. Is the following. This is a plot that I'm just report for you, and then you can. So this is T bar, and this is N divided by NC, so it is 1 over V bar, and you have a sort of line like this, and here you have many points corresponding to many different types of particles or molecules. Okay, so I can show you the plot here, and then you can see from the book. Okay, so this is the line I'm drawing, which is a relation between critical temperature and critical volume, if you want. Sorry, is a relation between scale temperature and scale volume, and those dots correspond to different molecules. So you see that they are lying very close to this theoretical curve, which means that basically you can describe all those systems with an equation of state like that one, okay? Independently from the values of A and B. It's a general feature. Ok, so this is an example of universality. Non so se riuscite a vedere la figura, vabbè, comunque si capisce che c'è una linea continua e ci sono i puntini, they correspond to neon, argon, xenon, methane, oxygen, etc. Okay, so they behave in a very similar way, at least for what concern the liquid gas phase transition. Now let's come back. Dove sta il tappino? Qua il tappino. So this van der Waals model, at the end, it has some power, because we at least can reproduce in a model like it is this behavior, which is the critical behavior, let's say. So having these lines like this one. So this was T larger than Tc, and this is T equal to Tc. So up to this point, the van der Waals gas is correct. It provides a good qualitative description of the physics of the phase transition. Now, what happens below Tc is actually a little bit tricky, and one has to consider this in a little bit more detail. So below Tc, let me draw the line here. We have something like that. So for a temperature T smaller than Tc. Let me write this point as A, the minimum, and B is the maximum. Now this is a feature of the van der Waals equation of state. The question we can ask ourselves is that if this feature is correct or it's something weird. Actually, this is weird in the sense that if you look at this region here, and you try to go from B to A, it seems like that when moving from B to A at fixed value of the temperature, it seems that if we compress the gas, so if we reduce the volume, then also the pressure is reduced. In all this region is what happens. And indeed, the way to say in a formula, and what I'm saying in words, is to define what is called isothermal compressibility, which is the following quantity: minus 1 divided by the volumes, partial derivative of the volume with respect to the pressure at fixed T. This is called isothermal compressibility. And the isothermal compressibility for a system which is stable from the mechanical point of view, for a system which is stable, on what concerns this isothermal compressibility must be larger than 0. It must be larger than 0, which means that if you increase the pressure of the gas, if you compress the gas, so if you reduce the volume, the pressure must increase. So then this derivative is negative, and with a minus here, this is positive. Okay. So because this is usually what happens if you try to compress a gas, so to reduce the volume, then the pressure of the gas will be larger. Whereas in this case, it's just the opposite. So here we are compressing the gas, we are reducing the volume, the pressure is also reducing, which is an instability. It's a mechanical instability. Okay, so here kT is less than 0, and this is a sign of mechanical instability. Because the system will collapse since you compress it and then it will reduce the pressure, so it will be much easier to compress it. So this is a mechanical instability that is not it's not physical, or well, better to say, it's not something that we can deal with in thermodynamics. Okay. So in a system in thermodynamical equilibrium, because thermodynamical equilibrium is a general statement that concerns mechanical equilibrium, chemical equilibrium, and thermal equilibrium. So now in a situation like that, we are moving in a region which is beyond thermodynamics. In thermodynamics, we cannot deal with this mechanical instability, so we can actually see what happens in a system which is in thermodynamical equilibrium once this mechanical instability has somehow provided its effect. Well, indeed, what happens, and we'll describe this in a moment, but just after a break, what happens is that is just this mechanical instability of the van der Waals gas that at the end provides the phase separation. That means that if you take the equational state like it is, it predicts this mechanical instability that actually is not present in thermodynamics, which means in a system in thermodynamical equilibrium. And what actually the model is hiding in itself is the fact that actually is much better from the second principle of thermodynamics to have a separation of phases. So we can somehow cure this mechanical instability by having a separation of the phases, in particular the liquid and the gas phases, because this is what we are trying to describe with the van der Waals gas. Okay, so this mechanical instability actually drives in this model the separation of phases. Separation of phases means the formation of a mixed phase, which means a first order phase transition. So then actually the van der Waals gas model, which is very simple, it can provide qualitative description of the critical line, and also it can provide, but we need to work a little bit on that, also can provide the main features of a first order phase transition like the liquid gas phase transition. But we will see this in a moment. So let's stop for a while, for say 5 minutes or so, then we continue. I'm going very slow. Passavo un pochettino la finestra.
Ma perché ti spiego di più, anche nel nuovo cambiamento, perché le cose che mi chiedeva non erano delle assunti, sono state delle precisioni che io non ci pensavo neanche per me di discutere. Precisioni matematiche che una 25 non mi importa certo prima si spiega se si fa di sapere solo perché quello è non ci sono niente quello che diciamo di cose anche dall'inizio del mio quindi perché allora, quando mi è andato benissimo, mi è un po' alto, torno accidenti, rifiuto. Perché proprio per cui ho iniziato a dire cose 18, 18. Invece no, il 18 ho fatto il nome malissimo, proprio quell'anno, e sono tanti anni. Come è andato proprio, non aspettavo. Ma è fatto diverso. Sì, lui è stato soddisfacente invece, perché lui ti fa parlare, fare come che tutto, fa parlare, fa ragionare, cerca di ascoltarti. Diverso è stato vicino, adesso di fare prima. Cioè, non l'ha fatto, io guardavo da gennaio gli appelli, le iscrizioni non ci sono più zero, no, perché 18 avevo scritto io, era primissima, che ho fatto. Sei contento di incubire la funzione, perché non sto drammatizzato. Infatti, io ero preoccupatissima per i bidotti, non avevo neanche per i bidotti, non avevo detto per caso, non avevo detto per un po' di Alle 11, perché la riunione dell'inizio minuti fa. Ma io ero fatta 2 ore di padella, alle 11. Perché ho detto ok, no, perché avevo l'ansia, quindi non avevo fatto niente. Ma io non so fare, perché l'ansia non è più.
No, ma l'altro non si deve iniziare con la prima di cosa.
Abbiamo intenzione tornando stante
Sì, no,
fisicamente. Non penso, dobbiamo fare tipo una relazione degli strumenti di storia e
quello per l'intervista.
esatto, non so, non so, abbiamo deciso così. E mi ero partita con l'idea di comprare farlo in una settimana e togliere le cose e vedere come si per distrutto di cose. Non incontravo come non ricordarlo di
Infatti mi ero chiesto quello che però era, cioè era tipo un corso obbligatorio per gli ingegneri. No, io poi il primo esame da una vita ero con tanta gente e sembrava in ordine alfabetico. Io non so cioè avrei fatto la mezza in un corso di vabbè, dopo. Io mancavo ok.
Perché non mi faccio vedere con ordine alfabetico.
Io fino a anno siamo classe però volevo sempre perché io la voglio leggere.
Così non era.
Dopo oddio, scusa. No, però l'ho messo io dentro il viola.
Okay, so let's see what this mechanical instability of the van der Waals equational state is telling us. It's telling us that something happens which cannot be described in thermodynamics, but in thermodynamics we can deal with the equilibrium states. And actually, this is what we are going to do now. We're going to present what is called Maxwell Construction for dealing with this instability, and we'll see that actually this provides the phenomenological explanation for the separation of phases in a first-order phase transition. Okay. Okay, so let us start with this. Remember that the devo andare a prendere un pennarello. Col verde si vede, vediamo. You see the green line, or is better? Okay, the blue maybe is better, but let's try. You see what I'm writing because I finished the blue one.
Sì, si vede abbastanza.
Vede, ok, provo a scrivere largo. Perché con i pennarelli ho questo problema. Perché non facciamo una petizione per avere delle lavagne normali? Cioè, non lo so, è da anni che lo dico. Ci hanno messo queste lavagne che sono una cosa più inutile. Anyway. Okay, so let us remember that dA, where A is the Helmholtz free energy, is equal to minus P dV minus S dt. And which also means that the partial derivative of A with respect to volume at fixed temperature is equal to minus P, and the partial derivative of A with respect to temperature at fixed volume is equal to minus the entropy. Now, from this equation in particular, the first one, we see that A is equal to minus P dV integrated over an isothermal transformation. Isothermal path, if you want. Okay. So I can produce the Helmholtz free energy by following an isothermal path integrating PdV with a minus, okay, from the first relation. And this is what actually we are trying to do graphically, in the sense that, let's try to do this. Now we have seen that for T below Tc, or when drawing an isothermal, what we get from the van der Waals gas is the following. Let's try to do the plot in a decent way. This is P, this is volume. Ok, facciamolo così. Then we have, suppose that we have here a certain value of pressure, P. And let's call it this intersection V1, and this is V2. And let's call this area S1 and S2, the area between the dashed line and the PV line, okay? Now we try to integrate this curve in order by following this relation. So we do the integral of this curve graphically, and we obtain the Helmholtz free energy as a function of the volume. And what we obtain by considering this equation is the following line. Cerchiamo di farla di nuovo in un modo decente. Okay, let's try to do it this way. Start with two volumes. Then we have something like that. And let's call this point A1, and this point here A2. Ok, il disegno non è che sia proprio bellissimo.
C'è una cuspide 1?
No, no, no.
Diciamo 2.
Facciamolo meglio. Non è facilissimo disegnare questo qua. No, no, è the line are continuous. It's just that I'm not able to draw enough. Or something like that. Okay? It's continuous. Now, what happens here in these points A1 and A2 is actually the following. Nothing serious, but for the fact that the tangent of this curve, which is the derivative of A with respect to the volume, is the pressure. Okay? And consider that in V1 and V2 we have the same pressure, which means that in A1 and A2 we have the same tangent. And of course now plot is very bad. Questa è la parte più difficile del corso, fare questo disegno. Facciamolo così, forse è più facile disegnare la prima la tangente. Okay, like that. And here is the tangent. This is the tangent. If I have a plot on the book, I will show you. But what happens here clearly is that in A1 and A2, the pressure are equal because they correspond to those 2 points here, which graphically means that the tangent of this curve in those points are, the tangent is the same. Okay? So now what we can observe is the following. So in A1 and A2, so first point, in the point A1, A2, what we have same temperature, because they are isothermal lines, both this and this, we have fixed the temperature, same pressure, which is the tangent here, or from here you see that they have the fixed value, the same value of the pressure. So that means that we have two phases, so two states, if you want, of two phases. Now we can states, which are actually phases, which are in mechanical equilibrium because the pressure is the same. They are in thermal equilibrium because the temperature is the same but different values of A1 and A2, or if you want, different values of V1 and V2. Okay, so we have, for a fixed value of pressure and temperature, we have two states which are called actually phases because we are talking about the same kind of matter, but that's better to call it phases, which have the same pressure, the same temperature, but different values of Helmholtz free energy and different values of the volumes. This is exactly what happens in a mixed phase. Okay, we have a fixed temperature, fixed pressure, but we have ice and water, or we can have both bubbles of vapor and liquid. Okay, so this simple model is actually describing the separation of phases. Okay. And so the fact that we can have, for a certain value of pressure and temperature, two phases with different volumes and also different Helmholtz free energies. This is the first thing one can notice. The other one is the following, is that this consideration holds true for the point A1 and A2 with volumes V1 and V2. Now what happens in the middle? exactly in this instability region, mechanical instability region, we see that between V1 and V2, okay, which was the unstable region, mechanically unstable region, or if you want, because A1, between A1 and A2, actually, there is a way to minimize the Helmholtz free energy in the following way. We can minimize A equal to A1 plus A2, so the total Helmholtz free energy sorry, this is not correct. We'll comment in a moment. We can minimize, let's call it A, the total Helmholtz free energy, in the following way. If I follow the van der Waals line, which is mechanically unstable for what we said here, I should follow this line here along the A-book line. But actually, you see that if I follow instead of this line, the tangent, I get a minimum, I get a, say, a smaller value of A. Okay, so if I connect A1 and A2 by following the tangent, I minimize A. So instead of staying on this branch, I can move on this branch because it realizes a minimum of the Helmholtz free energy, which is the second principle of thermodynamics. So, and if I connect A1 with A2 by following the tangent, I can write basically in a formula that A, so the total Helmholtz free energy, is a linear combination, not because it is a tangent, it's a straight line, and A can be written as a linear combination of A1 and A2, where I introduce a parameter chi that characterizes the straight line, which is the volume fraction of phase one, and one over the one minus the volume fraction, which is the volume. Sorry, let me be more specific. I have introduced chi is the volume fraction of phase one in the mixed phase. And of course, 1 minus chi is the volume fraction of the second phase. This equation here is the equation A equal to chi A1 plus 1 minus chi A2 is the equation of the tangent, which is basically the equation of state of the mixed phase. So basically what I'm doing here is that to realize first that A1 and 2 corresponding to V1 and V2 are two phases of the same matter at the same pressure, at the same temperature, but having different values of volumes and values of the Helmholtz free energy, first of all. Second, I know that this branch is unstable from the mechanical point of view, and I cannot deal with it in thermodynamics. I know instead that in thermodynamics, so in a state of equilibrium, the second principle of thermodynamics is telling me that I need to minimize the Helmholtz free energy. How do I minimize the Helmholtz free energy here? Well, by connecting A1 and A2 with a tangent, with a straight line, which is this tangent, which I remind you means that the pressure is the same, is always the same, okay, here, because the tangent is just the pressure. So I have a situation in which, again, the temperature is fixed, the pressure is fixed. What I change here is just the volume fraction of one phase with respect to the other. So far, this equation here describes exactly the mixed phase. It describes the mixed phase, which is this mixture between, let's say, a solid and a liquid, or a gas and a liquid, etc. Okay? And is provided by the second principle of thermodynamics, as usual. Now we can finish this topic just by noticing the following. Diciamo, cancelliamo questo. Now, in the point V1A1, the pressure, let's call it P, is minus the derivative of A1 with respect to V1 at fixed temperature, and this must be equal to minus the derivative of A2 with respect to V2 at fixed temperature. This is the equation of mechanical equilibrium, that is in here. And so this is one thing that we wrote already again. Now, which is the equation of the tangent? I have to do A2, so this is V1 and this is V2. A2 minus A1 divided by V2 minus V1, which is the angular coefficient of the tangent. No? So let's call angular coefficient of the tangent is A2 minus A1 divided by V2 minus V1. This is the partial derivative of A with respect to V along the tangent, and this is called, and this is minus P. Okay? Along the straight line, this is just the angular coefficient. Now, from this equation, I get that P times V2 minus V1, so P times V2 minus V1 must be equal to minus A2 minus A1. So I put this in here, and I have to add a minus there. Okay, and this is also equal minus E2 minus A1 must be equal to the integral of PdV from volume V1 to volume V2 at T constant. Okay, what I'm doing, I'm writing the angular, I'm writing the pressure in different forms. The pressure and the relation between pressure and Helmholtz free energy. So I'm following this line here. Okay. Now this line tells me that the angular coefficient of this line is just the pressure minus the pressure is provided by this formula. Okay. So I get that this is equal to this. But for what I said before, the Helmholtz free energy can be computed from the integral of the P curve in the PV plane, so this integral here, along the isotherms. Okay? So now I can conclude the following, which is just a graphical construction, which I do maybe where? Maybe here. Now, what is P times V2 minus V1? Let me do the plot again. In this expression. If I do P times V2 minus V1, I just have the area of this box. Okay. Where here we had S1. Whereas if I do the integral from V1 to V2 of PDV, I just have the area so let's say that this area is P V2 minus V1. This was S2. And if I do this integral here, it's just the area between V1 and V2 below this curve. Okay. So this area here is the integral from V1, V2, PDV. Okay. Now, this equation is telling me that this area is equal to this area. And you see graphically that in order this to be true, that means that S1 must be equal to S2. Now you see from the difference of this. Okay. Since they are equal, S1 must be equal to S2. So you see it graphically. Because here S1 is missing, whereas here is missing S2. So this is the so-called Maxwell construction. It's a graphical construction. That provides me a phenomenological way to cure the mechanical instability predicted by the van der Waals equation of states, which is the following. Suppose that I take a line here with T smaller than Tc, for which we have this nice behavior. Then what the Maxwell construction is telling me is that I have to set up here a value of the pressure for which the area S1 and S2 are equal. Okay? So then I have, if you want, to move the pressure, the value of the pressure, until I find a specific value of the pressure for which the area is below the pressure and the curve P as a function of V, and the area above the pressure and the same line are the same. But this is S1 and this is S2. Okay? So the pressure corresponding to the phase separation which of course means also the pressure corresponding to the phase transition, is obtained by imposing S1 equal to S2. And this is called Maxwell construction. Or another way, one can draw the curve Helmholtz free energy as a function of the volume and find the value for which the tangent, there is a cotangent. Okay, so you have to find, let me do the plot here. This is the easiest way to do it. You draw a van der Waals line and you choose the value of the pressure in such a way that these two areas, S1 and S2, are equal. Or another way to do it is, again, the Maxwell construction, is to draw A as a function of B. We said before that we have something like that. And we need to find the right value of the angular coefficient for which we have 2 points of tangent. Okay, or something like that. Okay, this is more difficult to do it, and this is much easier. Okay. So in conclusion, let me summarize, and then we stop it here for today, and we will continue next time. To summarize what we have done, we have introduced in some way, in a phenomenological way, interaction in our model. These interactions are providing the main features of interparticle interaction, which means attraction and repulsion, attraction at large distances and repulsion at small distances. We have kind of motivated the choice of van der Waals, which is an hardcore repulsion, infinite repulsion, and an attractive potential, which reduces the value of the pressure. Then we have obtained a relation between PV and temperature, which looks like the relation of the ideal gas, but with the important feature of having a critical point, so a critical temperature, a critical pressure, and a critical volume. And below the critical point, we have found this mechanical instability that can be cured by doing this Maxwell construction. Okay, so basically what we are able to do with the van der Waals equation of state is to phenomenologically describe this line here. Okay, this line here, in which we have a first order phase transition here, in which we have the phase separation, and in particular, those values of the pressure can be found for different values of the temperature just by doing a Maxwell construction. Okay, now the Maxwell construction provides me a way to find the equilibrium pressure between the phases at a fixed value of temperature. Okay, so I can find this line. And also I can find the critical point in here, above which we have a normal behavior of the van der Waals gas, which to some extent is more similar to the ideal gas, because we don't have any so we don't have these features that we had for the critical point and below the critical points. Okay, so this is just a, let's say, simple model with simple assumption, which however allows us to obtain already some interesting phenomenological results. Okay, maybe I just leave you with a small exercise, if I find it. Which is not related to this. For this, we will do an exercise next week. Which is the following. We have a gas of massless particles. Like photons, for instance. One can show, and we will do it, that the internal energy for massless particles, massless and non-interacting particles, interacting. One can show that the internal energy U scales as A. What we have here is the volume, temperature to the power of 4, and that the pressure scales as A divided by 3 to the power of 4. We will prove these two equations later. And one can do the following exercise. With these relations between U, P, V, and temperature, find the adiabatic index. And the adiabatic index was the following. Is the gamma in such a way that PV gamma is constant. Or if you want, is the ratio between the specific heat at the fixed pressure and the specific heat at fixed volume. Maybe some of you knows already the answer to this. The adiabatic index of massless or a gas of photons. You know, which is an ultra-relativistic gas. Should be 4/3. So gamma is 4/3. If you try to find, to solve the exercise, you can try to do it.
Più la gamma costante?
Sì. And well, the way you do it could be the following. Just consider the first principle of thermodynamics. dQ is equal to PdV plus du, and for adiabatic is equal to 0 for adiabatic. Okay, then you can write a relation between PdV and U by knowing that expression is the following one. Okay, so you can find the adiabatic index of this gas, and you can find, well, make a plot of the corresponding Carnot cycle, which is done by 2 adiabatics and 2 isothermal lines, and find the efficiency. The efficiency is, I remind you, is 1 minus the absolute value of Q1, which is the heat which is provided from the system to the thermal reservoir, and Q2 is the heat absorbed by the system. Okay, so this is a little exercise that you can try to do, and if you are interested, you can do it together next time. Well, in principle, one should find also that the efficiency of this cycle, of the Carnot cycle, which makes use of a different gas, because the equation of state we are providing here is not the standard equation of state, for which we have the adiabatic index is 4 divided by 3. It's a different one with a different adiabatic index, but actually the efficiency is always the same of the Carnot cycle. So it is 1 minus T1 divided by T2. Okay, so this is just a small exercise on the previous part. I want to try to do it. And I think I'll stop here because you also have 2 more hours. And see you also next Tuesday. Bye-bye. Devo spegnerlo qua.
Arrivederci.
Grazie.
Arrivederci.